When you're doing chemistry, sometimes you'll see reactions with one arrow, and sometimes you'll see with a forward and a reverse arrow. So if the reaction only has a single arrow, that means that it's not reversible and only the forward reaction is going to happen. But if the reaction has double arrows, meaning forward and backwards, that means the reaction is reversible. So both the forward and the backward reactions could occur. When you see that double arrow, that means that it's at chemical equilibrium. And the problem with equilibrium is that you hear the little word equal inside that word, and so it's tempting to think that it means you have equal amounts of products as you have reactants, and that's not what it means at all. Chemical equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. So notice that the key word there is rate, that's why I have it in capital letters. When you see equilibrium, you need to think of the word rate. So you could have a whole lot of reactants and just a little bit of products, but if the forward reaction is happening at the same speed as the reverse reaction, we say that it's at equilibrium, even though the amounts of reactants and products are not the same. So again, the word equal has nothing to do with the amounts of things, it's how fast the reactions are occurring. And when we talk about equilibrium, sometimes we can use a number to show us whether you have more reactants or more products once you reach equilibrium. So once the reactants are stabilized and you're going just as fast in the forward and the reverse reactions, you can see which one you have more of by the letter K. And I'm going to show you how to calculate this. K is called the equilibrium constant, and it's used to show whether the reaction lies more towards the products or more towards the reactants. So once it's at equilibrium, you have the equal rates of the reactions. You could have more reactants than products or more products than reactants, and you're going to use K to figure this out. K is equal to the products over the reactants, and those brackets means concentration. We haven't actually learned concentration yet. We're going to get there in our next chapter, so don't worry too much about what that means now. Just go ahead and put the brackets on your things. And notice that they're raised to the power of their coefficients. I'm going to show you how to set up that fraction in just a minute. One thing to keep in mind is that K only includes gases and aqueous things. It does not include solids or liquids. And there's two major mistakes that my students tend to make with this. The first is that since you read a reaction left to right, they always want to put the reactants on the top of the fraction because that's the first thing they usually write. So make sure you ask yourself, are you putting the products on the top or are you putting the reactants on top? And make sure you always do the products. And the second thing is they tend to forget to raise it to the power of their coefficient. And like I said, I'll show you how to do that. The reason we calculate K is that it tells us whether we have more products or more reactants. So if K is greater than 1, that means the top of the fraction is bigger, which is the products. So it tells you that you have more products than reactants. If K is less than 1, it means the reactants have more, because in that fraction, if the bottom of the fraction is bigger, then it's going to be less than 1. So this tells us that we have more reactants. So a lot of times you'll be asked to calculate K, and then you'll be asked what that means. So if K is greater than 1, it means you have more products. If K is less than 1, you have more reactants. So if this is our reaction, we're going to set up the fraction for K before we actually calculate it. So what you're going to do is take the products, in this case you just have one, it's NH3, you're going to put it in brackets, and you're going to raise it to the power of the coefficient that it has. So since there's a 2 in front of it, you're going to raise it to the second power. So this is what I'm talking about right over here. Put the products on top, and take that coefficient and make it an exponent. On the bottom, you're going to put your two reactants, so we've got N2 and H2. N2 doesn't have a coefficient, which means it's just 1, so you can just raise it to the 1 power. H2 has a coefficient of 3, which is why it's raised to the third power. And if you're ever asked what is the equilibrium expression, this is what I'm looking for. It's just the fraction. You won't always have to calculate stuff. Sometimes you just have to set it up. In this question, they gave you the concentrations of each of these components. So once you have your fraction set up, you just plug in the numbers that you're given. So 1.8 for NH3, that's why I plugged that in here. 2 is for H2, so plug that in here, and 1.5 is for N2. And don't forget to keep those exponents on there. And then you just type it in your calculator, and you'll get a number, and that number will clue you into whether you have more products or more reactants. So remember, K is products over reactants. So if K is less than 1, it means the bottom of the fraction is bigger, so that means you have more reactants. If K is greater than 1, it means you have more products. And there's some examples with this on a worksheet that I passed out called Chemical Equilibriums. If you want to try a few more, take a look at that worksheet, and all the answers should be on there for you. And the last thing for this chapter is called Le Chatelier's principle. This says that when equilibrium is stressed, in other words, when you do something to a reaction, it's going to shift to relieve the stress and restore equilibrium. So sometimes pharmaceutical companies or various chemists want one product or one reactant a lot. So let's say you're trying to make some ibuprofen, and that's a product in your reaction. You want the reaction to shift towards the product side. And what I mean by that is you want it to go faster in the direction towards the products so that you create more ibuprofen so you can sell it. If we're at equilibrium, the two reactions are going the same speed, so we need to put stress on the reaction to force it to go one way or the other. And there's 3 ways you can change equilibrium. You can either change the amount of stuff that you have, you can change the amount of pressure, or the amount of temperature. So let's start with the amount of products or reactants. For these, what I want you to do is picture a seesaw, and if you increase the reactants, if you picture that seesaw going up on the reactant side, that means it's slanting from top to bottom, going from left to right, which means a ball would roll towards the right. And that's going to help you figure out which way it shifts. Whichever way the ball would roll on a seesaw, that's the way that it's going to shift. This is going to sound kind of crazy, and it's easier for me to explain if I can show you. So if this is the first time you're listening to the video, make sure you come see me at lunch and I'll show you what I mean by all this. When it shifts to the right, what that means is that you're producing more of the products. And to do that, you have to decrease the reactants. If a reaction shifts to the left, it means that more reactants are formed, and so the products are going to decrease. So whichever way you're shifting towards, the stuff on that side of the reaction is going to increase, and the stuff on the other side of the reaction will decrease. So these are the 4 things that could happen with reactants or products. You could memorize these if you want, but it's a whole lot easier if you can just understand how to figure it out. And the seesaw method is definitely the easiest way to remember it. So please come in and see me at lunch and I'll explain the seesaw method. If we're talking about pressure, that's a little bit different. So first of all, pressure only affects gas particles because they're the only ones you can press together. So they're only going to affect gases. And the way I think of this is that I personify the particles to make it more concrete for me. So if you think of the particles as the fact that they never want to be crowded and they never want to be lonely. If you're going to increase the pressure on a balloon, so you're squeezing that balloon, it's getting smaller and smaller and smaller, those particles are going to get more crowded, so they're going to shift towards the side of the reaction that has fewer particles. And by figuring out the particles, you're going to add up the coefficients. So you'll look at the coefficients on the left and the coefficients on the right. Whichever side has fewer number, it's going to shift in that direction. If you decrease the pressure on a balloon, the balloon can spread out and get bigger, which means the particles are getting more lonely. And again, particles don't really have feelings, I'm just personifying it to help you remember it. And if the particles are lonely, they're going to choose the side that has the more particles, so the higher number of coefficients. So you can't really memorize which way it shifts for pressure, you just have to understand how to figure it out because each reaction will be different. And the last thing is temperature. If you're trying to change the temperature of something, you want to treat heat as if it's a reactant or a product. And sometimes they'll put the heat in the reaction for you, and you don't have to worry about it. But sometimes they'll just write it as a number with a sign in front of it. And if the sign in front of the number is negative, that tells you that the reaction is exothermic, so heat is coming out of it, which means it goes on the product side. If the number in front of the delta H is positive, we're talking about an endothermic reaction, so you're going to put it on the reactant side. And then once you put it on the reactant or product side, you just treat it as if it was a reactant or a product. So you can use the seesaw method to get it to figure out which way it shifts. And there's a bunch of examples right here on this chart. If you haven't done this chart already, go ahead and see if you can fill it in, and make sure you come check your answers. If you have already filled in the right answers for this, you could take a piece of paper and cover up the chart, the blank chart, and see if you can check your answers and fill them in again. And I'll be happy to give you the answers to these in class anytime. If you want to stop by, I can show you the answers to these. The last thing is just about how K is affected by these stresses. Temperature is the only thing that's going to affect K. So pressure and changing the reactants and products actually are not going to affect K at all. You can figure out what happens to K based on which way the reaction shifts. So since K is products over reactants, if the reaction shifts to the right, that means you're increasing the products. So if you look at this fraction, if the top of the fraction gets bigger, then K is also going to get bigger. If the reaction shifts to the reactants, that means the bottom of the fraction is getting bigger, so K is going to decrease. And this was kind of a lot for today, so definitely if this is the first time you're watching the video, come see me so I can go over it once more with you just to make sure you understand it. There is a worksheet number 8 in your packet that has some more with Le Chatelier's principle. Feel free to try some of those and check your answers anytime. And that is all for thermodynamics. This is the end of this chapter.